And then I'll talk about some IGP scaling, route reflection and configurations, and what that does to routes and paths. And then lastly, if we have some time, I'll talk about some BGP mechanics, how to configure BGP and troubleshoot and things like that. So let's start off. What is BGP? Well, it's the Border Gateway Routing Protocol. Fantastic. We all know what it is, right? This is the typical definition that you see of BGP. It's an exterior gateway routing protocol used for inter-autonomous system routing. And the current RFC defining it is 4271. An autonomous system typically is defined as a single network that is under a single administration with a single routing policy. And this routing domain is assigned an autonomous system number, an AS number, or an ASN. Those are all the same things. So that's the typical definition, but still, what is BGP? So in normal language, BGP is the routing protocol that allows networks on the internet to signal to other networks on the internet what is the set of destinations that they can reach. The word exterior is used to refer to the fact that it's intended to be used between networks on the exterior, and inter-AS also is used to refer to the fact that it's between autonomous systems. So basically, BGP is a protocol that allows you to learn multiple paths to each destination on the internet, and then selects which path is best, and uses that path to forward traffic. Only one best path is sent to your neighbors. And if you look at this drawing that I have over to the left, this is the CADA AS Internet graph. Each square represents an autonomous system or a BGP network on the internet, and the lines in between them indicate one or more interconnections between those networks where they're running BGP. So as you can see, there's a fairly dense mesh in the core, lots of BGP sessions, and that's basically how routes propagate throughout the network. So what's an autonomous system? Well, it's a single routing domain, and that's typically what people think of when they draw a cloud. But diving into that cloud, we have a collection of routers that typically have a common routing policy. They have a consistent view of routing. Usually it's a single IGP. Typically it's under a common ownership with common administrative control. And this network is assigned a single globally unique autonomous system number, for example, 64496. So where do ASNs come from? The globally unique ones come from the 5 regional internet routing registries: ARIAN, RIPE, APNIC, LACNIC, AFRINIC. There's some special ASNs. 0 and 65535 are reserved by IANA, so they're not supposed to be used. Private ASNs is that very high range from 64512 to 65534. Those are termed for internal use only and shouldn't show up on an AS path in the internet. And then there's also some documentation ASNs per RFC 5398, which range from 64496 through 64511 and 65536 through 65551. ASN format. There are 2-byte ASNs and 4-byte ASNs. The 2-byte ASNs range from 0 to 65535, but we're on the verge of running out of those, so we extended the numbering space and doubled it by adding another 16 bits. So this additional range ranges from 65536 through 4,294,967,296. And you'll note on the slide that I've written it without any commas or separation of any type. It's a large 10-digit number. There was a lot of debate about how to display these, and there were 2 basic camps. There was AS plain, which was, let's just display it as a large 10-digit number. These numbers are, you can count them, you can think about them very easily. But lots of people have said, even phone numbers, which are 10-digit numbers, have divisions. So maybe a long string of 10-digit numbers is not a good idea. So the other camp was AS dot notation, and what they suggested was it should be a 16-bit number followed by a period and another 16-bit number. So for example, the existing AS 1234 would be extended into the 32-bit space and become 0.1234. And the new additional range would start off at 1.0 and go up through 6535.6535. So there was a lot of unhappiness with this type of an arrangement as well. People didn't like to write regular expressions against this number set that's divided up. And in regular expressions, the period means a match of any character. So you'd have to use the backslash to escape all of the periods if you actually wanted to match on a period. And there was lots of debate about, maybe we shouldn't use a dot, maybe we should use a semicolon like IPv6 addresses. And then people spiraled out of control, and people said, well, how about a happy face? And pretty much now everyone has converged on AS plane, for better or for worse. There's also a special AS 23456. That's used to denote a 4-bit ASN for 2-byte only ASN-capable routers. So because you can't send a 4-byte AS in the AS path to routers that don't support 4-byte ASNs, instead you just send them 23456. Some caveats about AS numbers. Networks that are singly homed can use static routes to connect to the internet. These networks don't run BGP, they don't have an ASN. They basically don't count from the BGP perspective of the world. I'm not saying these networks aren't important or useful or good. They just don't exist when you're looking at the view of the routing table and counting up networks. Some transit providers also allow downstream BGP customers to use private ASs to BGP peer with only them, which they then strip off towards the rest of the internet. From an outside view, these networks don't appear, they're invisible. And this creates kind of an ownership problem because it looks like the transit provider is the one actually originating the route. So if there's a problem with that route announcement or routing with that route, it looks like that problem belongs to the transit provider, and that's who people will likely contact if there's an issue. The other approach is to use RFC 2270 ASNs. And basically what that is the transit provider goes to the RAR and gets a globally unique ASN, and they register it to themselves. But they register it in such a way that it denotes that it doesn't belong to them, but it's for use for their downstream customers that are singly homed to them. And then they allow as many downstream customers only connected to them to keep using this same AS over and over again. Wanted to do some quick BGP history just to let you know where we were coming from and what some of the issues were. So take you back to NFS days in '85. The NSF was established to connect 6 supercomputing sites together with 56K leased lines. They had PDP-11s that were running gateway software, which was written by Dave Mills, called the Fuzzball. And it ran EGP, Exterior Gateway Protocol, version 2. And the way EGP was built, it basically used a spanning tree algorithm, much like Ethernet does. And it expected that stub gateways would be connected to a centrally administered, centrally controlled backbone, which was the ARPANET. And it used an unreliable IP transport and a periodic refresh, so it sent the entire routing table as an update atomically. The problem was the network was growing very rapidly. It really wasn't a simple core with stub networks hanging off of it, as you can see from this diagram from '86. And it really wasn't scaling well. So in '87, NSF established an agreement with MCI, IBM, and Merit to upgrade the NSF backbone to phase 2. And as part of that, they deployed BGP. So enter BGP. This is referred to as the 3-napkin protocol. It was actually invented over lunch at IETF 12 between Yakov and Kurt with some help from Len. They basically wrote it down on 3 napkins. I understand those napkins do not survive. They had lots of ketchup on them. But they were immediately transcribed onto these 3 pieces of paper, which last I heard were framed at Juniper. And the 3 napkins were pictured here. The first napkin is the packet format. The second napkin is the description of codes and subcodes. And the third napkin was the finite state machine. And this was later formalized into RFC 1105 in June of '89. And that RFC was 17 pages. So a lot has changed in the IETF and RFC authorship since then. If you could imagine, BGP was a 17-page RFC. So, and obviously the rest is internet history. In '88, NSF was upgraded to T1s. Traffic was doubling every 7 months. In '89, it was upgraded to T3s. That's when BGP was deployed. It had 16 nodes at that time. In 1990, ARPANET was dissolved. It became BBN, and we saw the introduction of commercial ISPs, UUNet and PSINet, SurfNet, and NearNet. And then eventually in '95, NSFNet was dissolved. And if you have trouble sleeping tonight or the rest of this week while you're here, go ahead and download some of these RFCs and read them. They're great bedtime reading. This will show you the whole history from Exterior Gateway Protocol version 1 all the way up to the current BGP version 4. So let's jump in and take a look at BGP at the 30,000 foot level. So a couple of definitions to start things off. Neighbors or peers have a relationship between two routers. They're running BGP amongst each other. And there's a couple different types of neighboring or peering relationships. The first is transit. In this case, the network is usually a customer of an upstream transit provider, and the network usually pays that upstream transit provider to carry their traffic to all of the internet. Peering, usually denoted with a capital P, indicates that the two networks are roughly of equivalent size, and it's mutually beneficial for their customers to exchange routes between them. So you can imagine AT&T is not going to buy transit from Verizon. Verizon is not going to buy transit from AT&T, but AT&T customers would like to be able to talk to Verizon customers. They do that through this peering exchange. And then the third type of neighboring or peering session is a customer relationship. In this case, the network is a transit provider, and he's offering BGP to his downstream customer, who's usually paying them to carry their routes. Default routing is when you have an all-zeros route, which is your gateway of last resort. That's where they'll send traffic if you don't know where it should go or you don't have any more specific information of where to send that traffic. And the default free zone is an area, a collection of networks that have no default route. So these networks basically carry reachability to every single destination on the internet. And if they don't have a route for that destination, they simply can't deliver the traffic. So on a high level, what does this look like? So we're going to look at how routing information propagates from various different customers in this drawing. Customer one in this case is a customer of AT&T. He sends his route to his upstream provider, and AT&T will forward that route to its downstream customers, in this case customer 2 and Allstream, and it also sends it to its peers, in this case UUNet. Allstream will also send the routes that it learned from AT&T, which is its transit provider, to its customers. Verizon will send the route that it learned from its peer AT&T to its customers, which is Allstream, customer 3, and customer 4, but he won't resend that to another peer, in this case level 3. If we look at customer 2, we have much of the same thing, except he's got two upstreams. He's got AT&T and Allstream. AT&T will send it to their downstream customers as well as peering. Allstream will send it to its 3 transit providers, AT&T, Verizon, and level 3. And because level 3 is learning it from a customer Allstream, he'll send it to his customers, which include customer 4 and BT will send it to its customer, customer 5. Level 3 will also send it to its peers because it learned it from a customer. And then UUNet will also send this route to its downstream customers, but it's questionable as to whether or not it sends it to its peers. And this depends on whether or not the best route UUNet heard was from a customer or from a peer, because peers don't generally give transit to other peers. So if the best path is from Allstream, which is its customer, in that case it will send it to peers like level 3 and AT&T. But if its best path was learned from AT&T, which is a peer, it will not send it to other peers like level 3. So customer 3, much of the same. Sends it to its upstream UUNet that goes to all of its customers and peers. Allstream sends it to its downstream customer, AT&T to its downstream customers, level 3 to its downstream customers, same for BT. Customer 4 has 2 upstreams, UUNet and level 3. Level 3 sends it to all of its downstreams and peers. BT sends it to its customers. Allstream, because it's learning it from its transit provider, sends it to its customer, level 3 to its customers and peers, and AT&T to its customers as well, but not to peers. And lastly, customer 5 sends it to BT, who sends it to level 3, who sends it to its customers and its peers, and those networks send it to their downstream customers as well. At a high level, that's how BGP route propagation works. It's distance vector routing. The examples on the previous slide basically showed the distance vector nature of BGP. In addition to announcing reachability information for the destination, it also has a protocol next hop. And that protocol next hop, by default, is changed at the eBGP boundary. I have a slide on this in a minute. Each AS chooses its best path and then forwards traffic towards that protocol next hop. So this is kind of the distance in the vector of BGP. It's slightly more complicated because the BGP path selection is actually much more detailed and has a lot more factors in it, and we'll talk about that at the very end of the first section. But the point here is that an AS in the middle of the topology does not know the entire topology. It's only seeing the distance to the edge of its network, and it's only seeing the best path of all the downstream networks that are sending it. So in terms of forwarding, we've got all these next hops that have just popped into this diagram. And we'll note here that customer 2 has a path for 100.4.4.0/24, which is customer 4, with its next hops H and K, H being Allstream and K being AT&T. And you can walk this back through the entire network. AT&T learns that prefix with the next hop of G, which is UUNet. Allstream learns it with next hops F, C, and J, which are UUNet, the level 3, and AT&T. Verizon sees it from B and D, which are directly from the customer, as well as level 3. Level 3 sees it directly from the customer A, as well as E from UUNet, and so on. So link state routing protocols are the other type of routing protocols, and these are like OSPF and ISIS. And the way these work is every node in the network announces its reachability to every adjacent node and what that cost is. This gets flooded through the entire topology, and then routers, from their unique perspective in that topology, build a graph to figure out what the cost is to get to every node. So the way this works, we're going to look at announcements from A to F. Router A basically comes online and says, I've got 2 links to adjacent routers C and B, and my cost to get to C is 8, and my cost to get to B is 5. And it builds an update, and it ships that out all of its interfaces towards all the other routers that are in the IGP. And those routers receive that update, and they flood it out of all of their interfaces as well. So router B sends it to C and D, C sends it to E, F, and B, E sends it to F, D sends it to F, and you start populating the routing table on F. So F now knows the cost to get from A to B is 5, the cost to get from B to A is 5, the cost to get to A to C is 5, and from C to A is 5. And each router does this independently, and as they fly it throughout the network, you build up the entire routing table. So now any router in the routing table can build this tree and figure out what is the shortest path to get to any destination. In the event that there is an outage or a break, for example, the link between A and C goes down, then router A simply sends out an announcement saying, I no longer have a link to C. And he'll flood that out, all of his interfaces that will reach router B. Router B will flood that to C and D. C will flood it to E and F. At this point, F prunes that out of his graph, and he then calculates the new shortest path to get to the destination. So link state versus distance vector, what's the difference? Well, link state protocols only need to flood information about what link or node has gone down. So it's very fast. The flooding can be independent of calculating the best path. Each node simply prunes off links that are no longer in service or adds new links that suddenly are in service and then calculates a new best path. And they converge very quickly because they don't depend on a change of topology to be recognized before they flood. So it floods very quickly, and then each router simultaneously calculates the new topology. The drawbacks to this is that each node has a full view of the topology. It doesn't scale well for large networks. It carries a lot of state, and each node, at least at each given level of hierarchy, will see all the instability in the network. So distance vector routing protocols, on the other hand, only need to send updates when the best path changes. So a distance vector protocol needs to first determine if the topology change creates a new best path, do path selection. If no new best path is selected, it simply does nothing. If there is a new best path selected, it has to build an update and send that update out. Each node does not have a full picture of the network, which means it scales much better for large networks. It carries a lot less state, and only nodes where the best path change need to be sent an update or a withdrawal. On the other hand, it takes longer for updates to cascade through the network because each node must process the update and withdrawals first, calculate new best path, and then decide if it has to send its own update. So why do we use distance vector routing for the internet? Well, because of the large-scale nature of the internet, routing tables lend itself much better to distance vector. It reduces the amount of state required. Networks on the internet are also run by different organizations, so no one person is responsible for the stability of the internet. And with distance vector routing, you can sort of isolate that instability to different areas of administrative control. So it reduces the churn and provides a level of separation. For internal topologies, they tend to be much smaller, and the smaller amount of state required for an internal topology can easily fit within the limits of a link state protocol. The internal topology is generally run by a single organization who has control over the stability of that network and can set standards across that network, and it converges very fast. So if you picked up a textbook in the 1990s and said, how do I build a network? Typically, they would give you this very bad advice. And that very bad advice was, run BGP as your exterior gateway protocol on the edge of your network, run an IGP internally, usually OSPF or ISIS, between your routers within your network, and then on the edge, redistribute all of your BGP routes into your IGP, carry that across the inside of your network, and then on the far end where you're running BGP, redistribute it back from your IGP back into BGP and announce that out to the rest of the internet. This doesn't scale. Your IGP becomes as large as the internet table, think hundreds of thousands of routes, and any instability in the internet gets translated into instability in your local network. And when you're redistributing from and back to protocols, you lose a lot of the metrics. So this is not a good design. Typically what people do these days is they run eBGP between the edge of their network and other ASs to learn internet routes. And then they run iBGP internally to ship those internet routes around within their inside their network. And then they also run an IGP, which is used to learn the internal topology of their own network. And there's a couple of different ideas of routes that you can put in the IGP. My recommendation is keep it as small as you possibly can, so that way it is the most stable and the quickest to converge. The smallest possible implementation is to put your loopbacks only into your IGP if you're running ISIS. You don't even need your back-to-back point-to-points in ISIS because it runs over CLNS, which doesn't require IP. If you're running OSPF, then you have to put your loopbacks and your backbone point-to-points into the IGP. That's the bare minimum. Some people will go a step further and say anything that is a BGP protocol next hop, put that into the IGP as well. Some people will add on to that any destination that requires IGP-based load balancing. I've got some slides on that in the second half. And some people will also add any destination that needs fast convergence. So maybe they'll take stuff out of BGP and put it into their IGP in order to allow it to converge faster. And then the least preferred is anything that's considered an internal route, any prefix that you own, put it into the IGP. Definitely not recommended. So good BGP IGP design really gives you the best of both worlds. You use BGP for the internet routing. It converges slower, but it has some level of isolation, and it allows the internet table to scale to hundreds of thousands of routes and millions of paths. And you use your IGP for your internal topology, which converges faster. The topology is kept small, so it converges quickly, and scaling is not an issue. And the stability of the topology is not an issue because it's 100% your network, which you control the stability of. So eBGP and iBGP, I've already talked about this a little bit. The basic difference here is eBGP is when your BGP neighbors belong to different networks, different autonomous systems. In this case, every best path is advertised across the eBGP boundary. eBGP neighbors are usually directly connected routers, and the protocol next hop is typically changed to the advertising eBGP neighbor's address. iBGP is when your BGP neighbors belong to the same autonomous system. They're part of the same network. If a path is learned via iBGP, you don't re-advertise it to another iBGP neighbor, which requires a full mesh of iBGP peering. I'll talk more about scaling that in the second half. iBGP neighbors are generally not directly connected, but they do share a common IGP, which allows them to reach each other. And they advertise every best eBGP path that they learn to iBGP neighbors, but like I said, they don't re-advertise iBGP paths. And protocol next hop typically is unchanged in this case because you're using your IGP to figure out how to get to that protocol next hop. So BGP protocol next hop. There's a number of ways that you can set protocol next hop within your network once you learn a route from eBGP. You can just leave the protocol next hop as it is, in which case it could be a directly connected interface, which is basically the far end of the point-to-point to the router you're neighboring with. If you're not neighboring with the far end router interface, but you're neighboring with a loopback, in order to make that BGP session come up, you'll have a static route. And that static route could then be reachability to the loopback of the neighbor, which could be the protocol next hop. Or you could rewrite next hop towards your iBGP to be yourself, in which case that route's going to be reachable through your IGP. So going through these, a route reachable in your IGP could be a number of different cases. It could be that your eBGP peering is not the local router. So you're looking at a route somewhere in the middle of your network topology, in which case you're going to have an IGP route to the edge router's loopback. It could be that the edge routers are peering with the directly connected interface and putting that directly connected interface passively into their IGP, in which case you'll have an IGP route to it. Or it could be that you have a static route to peer with the loopback, and that static route is being injected into your IGP as well. You also have these same flavors with it being another BGP route. Rather than injecting the directly connected route into your IGP or the static route into your IGP, you can redistribute those into BGP, and then you'll just do a two-level recursion. So you'll have a BGP route, which has a protocol next hop, which is reachable through a BGP route, which has a protocol next hop, which is a loopback of an edge router. So let me diagram what that looks like. So a route comes in for a lookup, and if that route is a directly connected route, you simply ship the traffic out that interface. Route comes in for a lookup, and that route is a static route. That static route either points to a directly connected interface, in which case you ship it out that interface, or it has some far end next hop address, like Ethernet on a broadcast medium, and then there's some layer 2 mechanism like ARP to figure out how to reach that layer 2 destination, and you ship it out that interface. Or a prefix comes in, and that route is reachable through your IGP. You look at your IGP graph, you figure out what is the shortest path to get there, you know what your outgoing interface is, you ship it out that interface. In the event that it comes in and it's a BGP prefix, then you have to look at the protocol next hop. One case is that the protocol next hop is the eBGP neighbor interface of the router that's eBGP peering with that network. But if you're not on that local router, you have to do a route regression. So the next hop could possibly be that edge router's loopback, or it could be the directly connected interface, which is being redistributed into BGP, which has a next hop of that edge router loopback. Both of those are in your IGP, so you regress down to the IGP, you know the shortest path in your IGP and the outgoing interface to send it out of. The other possibility is if it's on the egress router itself. If the next hop is the eBGP neighbor interface, well, that's a directly connected route. You send it out that interface. If the next hop is a static route, that static route points to an interface or to a far end destination that's reachable through, say, ARP. And this is just walking you through again in words the diagram that we did. So we're going to look at the three cases of the different protocol next hops. We're going to actually look at the state of the different routings and how this works. In the first example, AS100 is going to advertise to AS200 via eBGP. AS100 is going to use the AS100 side of the point-to-point link. And when the route is learned by AS200, they're going to continue to use the natural BGP protocol next hop. And the AS200 edge router learning the prefix is going to re-advertise it to its iBGP neighbors. And it's going to set next hop self. So the next hop is going to be reset to his own loopback. So let's walk through this. So this is the state that you see here on some router in the middle of AS200. You'll note that it's got a static route for 100.2.0.0/16 to discard. That's the pull-up route representing all of the space for AS200. That static route is going to be redistributed into BGP. On the eBGP speaking router, we have the same state. And when the static route is redistributed into BGP, he's going to send it to all of his iBGP neighbors, including the eBGP speaking router. So this is the route for the /16. And you'll see the next hop is 100.2.2.2, which is this router's loopback here. So this is kind of the setup in AS200. In AS100, this is the setup here. We've just got some routing information, how to get to these routers, as well as his uplinks to the core of AS100. When the route is advertised via eBGP, it's learned on the ingress of AS100. So this is the /16. And you'll see the next hop is 100.1.3.2, which is the BGP neighbor address. And he's going to set next hop self and advertise those routes to AS100. So on the far end of AS100, you'll note that we're learning the /16, and the next hop is 100.1.1.1, which is the edge router's loopback. We know how to get to 100.1.1.1 in the IGP, in this case ISIS, and we know what interfaces to use to reach it. Second example, we're going to redistribute connected into BGP. So the way this works is, again, the same setup. And we're going to learn the route via eBGP and redistribute our connected routes into BGP. So this /30 point-to-point here is going to be redistributed into the iBGP for AS100. And you'll see that here. Here's the /30 with a protocol next hop of 1.1.1.1, which is his loopback. We then advertise via eBGP the /16, which shows up here with a next hop of 100.1.3.2, which is the natural next hop of the BGP neighbor. And he's going to re-advertise that to the iBGP. And when he advertises the /16, it has a next hop of 100.1.3.2, which again is that same natural next hop. And we know how to get to 100.3.2 through 100.1.3.0/30, which was the directly connected network that we redistributed into BGP. So the third case we're going to do here is redistributing static into BGP, very similar. On this router, we do an IP route for these loopback /32 in order to make BGP come up. So we redistribute static into BGP, so that static route is going to show up on some other router in AS100 as 100.2.2.3/32 with a next hop of 100.1.1.1.1, his loopback. We then advertise via eBGP the /16, which shows up on the edge router with a next hop of 100.2.2.3, which is the loopback in this case. And the way that this router gets to the loopback is through the static route to 100.1.2, 100.2.2.3. Here, it's down here, 100.2.2.3/32, and we know the interface that's reachable through. We then re-advertise that /16 to the iBGP. Oops. And we have the 16 here with a next hop of 100.2.2.3. Again, this router's loopback address. And we know how to get to that address because it's been redistributed into BGP, 100.2.2.3/32 with a next hop of 100.1.1.1, this router's loopback. So in a nutshell, this is how route regression, route resolution works in the network for various cases. Generally, most networks will pick one flavor to run with for most of their interconnectivity. There's also third-party next hops. In this case, AS300 is eBGP peering with AS200 and advertising 100.3.0.0/16 with his next hop of 100.1.3.3, the interface on this Ethernet. AS200 is also eBGP peering with AS100, and he's going to advertise his /16, 100.2.0.0/16, with his next hop of 100.1.3.2. And he's also going to advertise 100.3.0.0/16 with 100.1.3.3 as a next hop. So he's advertising AS3's routes with AS3's next hop. This is a third-party next hop. This allows AS100 to not have a BGP session directly with AS300 and to efficiently deliver that traffic directly to AS300 without having it to go U-turning through AS200. But there's a danger in third-party next hops because they can be used when the third party is not on a shared LAN and doesn't want those routes advertised. So in this case, we have AS200 getting transit from AS100 and AS300 getting transit from AS100. And they're each advertising their own aggregate. And then you could imagine a denial of service attack happens where some address inside AS200 is getting attacked, and it's drawing lots of traffic, and it's flooding out the link between AS100 and AS200. So AS200 goes ahead and advertises that single /32 to AS100, but sets the next hop to be some address inside of AS300. Now, all of a sudden, AS100 is going to forward all of that DOS traffic to AS300, who turns out to be a competitor to AS200. So wanted to just briefly talk about the difference between routing versus forwarding. Routing is the process where information reachability about the destination is shared. A router might learn multiple paths for a given route. These routes are stored by the routing engine or the route processor in the routing information base or the RIB. It does path selection and it chooses the best path, and that's the one that's used for forwarding. So once the best path is chosen, that information is shared with the forwarding engine and is stored in the forwarding information base, the FIB. and you basically do a fib lookup and consult the fib table to figure out what interface to send traffic out of. So if we go back to the customer 2, customer 4 picture, these very light gray arrows are the route propagation information. But if we look at customer 2's perspective, he's got 3 equally good paths to reach customer 4. So there's one through AT&T and UUNet to customer 4, one through Allstream and UUNet to customer 4, and one through level 3 to customer 4. So customer 2 has to choose between these equally good paths to forward between. So we do that through BGP path selection. So at a high level, this is the BGP path selection overview. I'm going to dive down and go through these much slowly after I run through this slide. But I wanted to run through them really quickly once so that you could see in entirety what the path selection algorithm looks like. So the first thing you do is you check to make sure that it has a valid route, that route is reachable, and prefer routes that are more specific over less specific. Then you're going to prefer the lowest protocol preference or the highest Cisco proprietary weight, higher local pref, locally originated on Cisco, shortest AS path length, locally originated on Juniper. You can see the vendors implement things slightly differently. Lowest origin code, where IGP is better than EGP, which is better than incomplete or unknown. Lowest multi-exit discriminator, prefer eBGP learned routes over IBGP learned routes. Lowest IGP distance to the protocol next hop. Shortest route reflector cluster length if you're on a Juniper. Oldest eBGP path. Lowest router ID, shortest route reflection cluster length on Cisco, and lowest neighbor address. So these are all based on BGP attributes. So what is a BGP attribute? Well, a BGP message consists of one or more NLRI. Well, what's an NLRI? NLRI is a network layer reachability information. It's typically a prefix and its mask. So whenever anyone says, talks about an NLRI, they're talking about a prefix and a mask. When you send an update or a withdrawal or a BGP message, all of the prefixes in that message must share the same set of attributes. And the attributes are properties that describe the route or routes. And those attributes are encoded in a TLV type length value, which makes it easily extensible. So you just specify the attribute that you're adding is of this type, it is this long, and this is the value. So if you wanted to add a new TLV type, it's fairly easy to do. So BGP types, some are mandatory, which means it has to be in the update. If it's not in the update is not valid and you have to throw it away. Some are optional, which means not all implementations need to understand the attribute. Some are discretionary, which means it's not required to be in the update. Some are transitive, which means it can be shared between multiple networks. And some are non-transitive, which means they get lost at the eBGP boundary. So diving in now, the first 3 things I talked about were validity, reachability, and specificity. These are actually not part of the BGP path selection algorithm, but I've included them here for completeness. So the first one is validity. You want to make sure that the route that you're getting is not malformed. It might have an invalid attribute value. It might have a required attribute that is missing. And it might have a variable length attribute where it says the length of the attribute is this long and then it has this much data in it. So if those don't match up, clearly something is wrong. It's not valid, you throw it away. Additionally, we have an AS path, and the AS path records every network that the route has propagated through. And that's partly used for loop prevention. So if you see your own AS in the AS path, you consider that looped. You should know about that route directly from yourself. Throw those away. Same about cluster ID list. If your own cluster is in the cluster list, it's looped, throw it away. And then there's also some knobs as well. There's enforced first AS. There's this transparent route reflector thing that can send you an update and not include itself in the AS path. And that looks kind of bogus. So there's a knob that you can say, if the first AS is not the AS I'm peering with, throw that route away. And then lastly is this Cisco default value, which is synchronization. It used to be in, I think, up to version iOS 11, if you were learning a route and the next hop was not reachable in your IGP, you consider it invalid and you throw it away, unless you configure no sync, which virtually everyone did. So they recently changed that to be the default behavior in 12-something. So that's validity. The next is reachability. So you get a validly formed route and it's got a protocol next hop. can you actually reach that next hop? Do you have a route to that next hop? Is that next hop reachable through itself? Or is there no route to that next hop at all? If any of these things occur, you can't get there, the route's not usable, throw it away. And then the last thing is specificity. More specific routes are preferred over least specific routes. So if you have 1.2.3.0/24, that's better than 1.2.0.0/16. You can imagine if you're holding a letter and you want to mail it to Schuylkill, Pennsylvania, and 2 post trucks come by and one postman says, I know how to get to Pennsylvania, and the other one says, well, I live in Schuylkill and I don't know where that is. Which one do you think is going to be more reliable in delivering your letter? The one that has more information about the destination. Same thing with the routing protocol. The more specific routes are more detailed information about the destination, more likely to get you to that destination, so they're more preferred. Incidentally, this is also why prefix hijacking becomes a problem, because people will just start arbitrarily announcing a more specific route and suck traffic away. So protocol preference in Cisco proprietary weight. The lowest protocol preference wins, and the highest Cisco proprietary weight wins. So Cisco proprietary weight is a value that you can configure locally on the router. It's not part of BGP. It's not advertised to anyone else. The default value is right in the middle at 32,767, and you can manually make it lower, down to 0, or higher up to 65,535. You configure this through policy, either per neighbor, per prefix, via a route map, and weight is not propagated to other BGP routers. This is a fairly dangerous knob that generally people shouldn't use, but if you find you need to use it and you find that you have a multi-vendor implementation, you'll note that Juniper doesn't have the Cisco proprietary weight. So the way that you would create a similar behavior in Juniper is to manipulate the locally configured protocol preference on specific BGP prefixes, and you can do that through policy. So here is a table that just shows the relative weights of the different protocol preferences. Again, there is some differences between vendors, but generally they're more or less the same. OSPF is more preferred than ISIS. ISIS is more preferred than BGP, so on and so forth. Local preference. So highest local preference is preferred. The default local preference is 100. And local pref can be set by policy, and it can be used to modify outbound traffic. Local pref is sent to iBGP neighbors, but it's not transitive. It's not sent to eBGP neighbors. However, typically transit providers will offer a set of communities that allow a customer to indicate a local preference value that they desire. You slap that community on your prefix, you send it to your eBGP upstream transit provider. It matches on that community and sets your desired local preference. So in that fashion, you could use it to control inbound traffic as well. On Cisco, locally originated, routes that are locally originated and redistributed into BGP are preferred. So that includes the network statement on the local router. That includes routes that are redistributed from another protocol, like static or connected. And that includes routes that are created through the aggregate command as well. Juniper doesn't really redistribute from one protocol to BGP locally on the box, so it doesn't really apply. The next is shortest AS path. As a route propagates from network to network, the AS is added to the AS path. The origin is going to be all the way to the right, and as it goes through the network, each AS is going to be appended to that list, with all the way to the left being the AS that you're hearing the route from. Like I said before, the AS path is used to prevent routing loops, but it's also a rough measure of distance as well. There's a few caveats here. If you have an AS set, that only counts as a single AS. And if you have Confederate ASs in the AS path, those don't count at all. I'll talk more about Confederation in the second half. It's not a very good measure of distance, because it's possible that you can have some transit providers that have one large global autonomous system with a single AS. And you might have other transit providers that have multiple ASs spanning that same global space. So it's not the best measure of distance, but it's the only one that we have. So giving you an idea of what this looks like, we've got customer 4 sending his route to his 2 upstream providers, UUNet and level 3. When he sends it to eBGP, he adds his AS 400 to the path. When level 3 sends it out to their downstreams, Allstream and BT, level 3 adds 3356 to the AS path. And same for when he sends it to transit. BT sends it to their customers. You'll now see 3 ASs in the AS path, 5400, which is BT, 3356, which is level 3, and AS400, which is customer 4. Same for Allstream. Allstream will send it to its customer, and you'll see AS400, the origination. You'll see 3356, the level 3 path, as well as 15290 Allstream. And that's not the only path that exists in this topology. There's lots of other paths. For example, level 3, we'll see it directly from AS400, as well as from its peering session from 701. 701 will see it directly from the customer, as well as its peering session from level 3. AT&T will see it from its peering session with 701. Allstream will see 3 paths. He'll see AS400 behind 701 as well as behind level 3, and those are both the same length, so they're equally as good, and he's going to do path selection on something lower down in the algorithm. The AT&T path is much longer, so is not preferred. And then Allstream will pick one of those paths. In this case, we've chosen the level 3 path. And so Allstream will see the path behind, I'm sorry, customer 2 will see the path behind Allstream level 3 AS400. They'll also see the AT&T path. Then Juniper, yes, go to the mic, please. If you could.
Brian Johnson from Dickey World Networks. I know on Cisco you can turn off BGP AS path hops as a selection in the algorithm. You can turn it off. Can you do that in Juniper, do you know?
So you're talking about the loop prevention, turning that off, ignoring your own AS in the AS path?
It'll still do loop prevention. It just won't use it as a method to select the best path. So it sees them. If it sees a loop there, it discards. But then when it gets to the point of selecting what is the best path, it doesn't use it at all in the selector algorithm. Just skips over that, goes to the next step.
Yeah, I don't believe you can turn that off in Juniper. I'm not familiar with that. So Juniper will prefer locally originated paths. So it prefers strictly internal paths, IGP route static, direct, local, over BGP paths. And like I said earlier, Juniper really doesn't redistribute locally on the router from other protocols into BGP. It redistributes them towards exporting towards other neighbors. It's possible to do using import and export in RIBs, but very uncommon. After that is origin, where the lowest origin is preferred, and there's a lot of debate about origin. The way it used to be used is IGP routes redistributed from IGP were preferred, then followed by routes redistributed from eBGP, which was the eBGP protocol. This was in the days where we were migrating from eGP version 2 to BGP, versus anything else, whether it's incomplete or unknown. The two vendors call it something different. Incomplete or unknown basically means you redistributed it from something where you really don't know the state of it. So some people say you should never ever see eGP as a setting in origin on the internet because nobody uses eGP anymore. Other people say, well, in the spirit of what people were meaning, IGP is a dynamic protocol that is most trusted, eGP is any other dynamic protocol, and incomplete or unknown is any non-dynamic protocol, static links, for example, directly connected links. So some people will use it that way. It's also important to note that there's inconsistent default behavior on this. When you redistribute on different platforms, some will set it to IGP and some will set it to incomplete or unknown. So because of this inconsistent behavior, a lot of transit providers have come to the conclusion that origin is not actually used for anything. And although origin is supposed to be set by the guy that redistributes the route into BGP, they feel that they can freely stomp on it to influence path selection within their own network. So some transit providers will actually reset origin to make one route less preferred over another, even though per RFC they're specifically not supposed to do that. MED, multi-exit discriminators. So this is an inter-AS non-transitive optional attribute. So that means you can send a MED value to a neighboring AS, but it won't propagate beyond that AS. The lowest MED is preferred, and MED is intended to be used when there are multiple exits to a given destination, so that way the downstream network can indicate which entrance points are better than which other entrance points. One way that you can do this is you can set an arbitrary value. If you want a primary backup configuration, you can say MED on the primary is 10, MED on the backup is 20, and you can always force traffic to use the primary. Another way that this can be used is you can use your internal IGP metrics and set your internal IGP metrics to the med value towards eBGP. I have some slides on this later. Med values are only compared when the neighboring AS is the same. This is because it could be a function of the IGP metric, and IGP metrics coast to coast on one network might be tens of thousands and might be 35 on another network. So because these aren't really comparable values, you generally only compare meds between the same autonomous system number. And if a med is not set, it assumes a value of 0. The default value of 0 with med not being set turns out to be not so helpful, because if you want to start depreferencing links, you have to go and then preference up all the other links. So there has been some debate in the past about changing the default med value to infinity, or the largest possible value, or one less than the largest possible value. So some implementations may treat a different med differently, so do check that if you plan on using default med values. There are some options with med. There's always compare med. In this case, you will make a med comparison between two routes, even if the neighboring AS is different. There's also Cisco non-deterministic med. So Cisco does this pairwise route selection. So it takes the first route and makes it best, and then it takes the second route and compares that to the first route. And if the second route is better, that becomes the new best. And then if there's a third route, it compares the third route to the second route. And if the third route is better, that becomes the new best. You can get into a scenario where you have 3 routes, where the first route is better than the second route, and the second route is better than the third route, and the third route is better than the first route. And depending upon the order in which you've learned them, you might choose a different best path with this Cisco non-deterministic behavior. Juniper compares all the routes together, so it will always make the same decision. But if you wanted to have the same Cisco behavior on a Juniper, there's a knob to turn on Cisco non-deterministic med. I'm also going to diagram this later on when I talk about med oscillation. You get the exact same behavior when you have a hierarchical BGP network, but in that case it's persistent and it's really bad. Have some slides at the very end of the second section on that. So the next thing is prefer eBGP learned paths over iBGP learned paths. So here the idea is if you're learning the route from eBGP and you're also learning it from your own network via iBGP, and both routes are equally as good, prefer the eBGP one, because that will cause you to send a route update to the iBGP, so that way the network gets to see more possible paths. After that, it's lowest IGP distance. So look at the protocol next hop and calculate the IGP distance to that protocol next hop. Whichever one is shorter, that's the one you prefer. In the event that your next hop is not in your IGP, say it's BGP, then you do a route regression. So you look at that next hop, you pick the BGP route to get to that next hop, you figure out what the BGP route of that next hop is. If that's in your IGP, take the cost to that. In terms of static and directly connected routes, some vendors treat them differently. Some will give them an IGP cost of 0. Others will have there be a null value for IGP and make no comparison. So there are some differences here between vendors. At this point, you're getting to be fairly arbitrary in terms of what you're picking to be the best path, but you want it to have an algorithm that always comes out deterministic. So you need to have a path selection algorithm to actually pick a best path. So again, these things kind of get arbitrary, but the next one on Juniper is shortest route reflection cluster list. So prefer if 2 routes are equally good and one has a shorter cluster list than the other, take the one with the shorter cluster list. I'll talk more about clusters in the second half. For eBGP learned routes, prefer the older route. So basically what this means is if you're learning 2 paths via eBGP and one flaps and the other one is stable, just stick with the stable one. So some people think this is good because it reduces unnecessary churn. Some people think this is bad because it's non-deterministic. And the problem with it being non-deterministic is you might have a long persisting session with a provider where you learn a lot of routes from. It could be a peering session where you learn, half of the internet from it. And you have another peering session with another provider where you learn the same half of the internet, but it's not preferred because that session has been unstable in the recent past. And then you get a flap on the stable link. You do some maintenance, you take a router down, a link goes down for some reason. All of a sudden, all that traffic is going to shift over to the other peer, and you might not have had enough bandwidth to deal with that because you weren't prepared for that to happen. So if you don't want to use the oldest, you can override it with always compare router ID. Then you get to lowest router ID. So if you're eBGP peering with 2 neighbors, Each of them has a globally unique router ID, whichever one has a lower IP address. You pick that one. So 4.4.4.4 is a lower number than 8.1.1.1. So 4.4.4.4 would be better. And then Cisco does shortest route reflection cluster list, same as Juniper, they just do it in a different place. And then the final thing is the lowest neighbor address. So in the event that you have multiple BGP sessions to the same router, that router has one router ID. So the router ID from both of those updates is going to be the same. So you have to break on something even lower. In this case, it's the lowest neighbor address. There are a couple other attributes that I want to talk about briefly. BGP communities is the ability to put one or more labels on a route. Communities are transitive and optional, and they're defined in RFC 1997. It's a 32-bit number, usually represented as a 16-bit number, 16-bit number. Typically, the first grouping of numbers is the autonomous system number, and the second grouping of numbers is an action value. For example, 701:80 indicates that AS701 should set a local pref of 80 when it learns this route from a customer. 701.8:80 indicates that AS701.8 should set a local preference of 80 on this route when learned from a customer. It just so happens that UUNet and AT&T use the same :80 community. That's not a standard across transit providers. Some use different values, so you'll have to figure out what values are supported by each of your transit providers. Generally, BGP communities are used to classify a type of route and then write policy to manipulate that type of route. It's useful for information purposes, such as determining the location of where a route was learned, or tagging a particular type of route, say, I learned it from a peer, don't advertise it to other peers. Extended BGP communities. So RFC 4360 extended the BGP community space to a 64-bit number. The first 8 bits indicate the type, whether it's a regular or extended community, and it can also indicate whether the community is intended to be transitive or non-transitive. And then for the extended communities, the second 8 bits indicate the subtype. It could be a 16-bit ASN with a 32-bit target value. It could be a 32-bit ASN with a 16-bit target value. And this is useful to encode 32-bit ASNs. So if you wanted to encode, 1.1 is your ASN, some action, :80, you could do that. It's also useful to extend the action space to have more numbers in it so you can designate more things. People tend to like to use groupings of numbers to mean something, like the 1,000 range is used for national stuff and the 3,000 range is used for customers. And then finally, it's also useful for VPNs to signaling route targets. So the way this works is you might have the same route show up in 2 different VPNs. Toyota might have a VPN and Ford might have a VPN, and they both might be using the same 10 space. So to distinguish between whether it's 10/8 in the Toyota network or 10/8 in the Ford network, you basically use a route target identifier to say which virtual routing interface it belongs to. There's a few well-known communities. No export, which means don't advertise it outside the local AS. So you can set no export on a route, send it to eBGP. The upstream AS will learn it, but then they won't send it to the rest of the internet. No advertise. You can set that on a route, send it to your upstream eBGP neighbor. That router will learn it, but it won't advertise it to any other routers, not even the iBGP. No export subconfed. You can advertise that into a router, and he will keep it local to his subconfederation. I'll talk more about what subconfeds are in the second half. And no peer, which indicates do advertise this out to other customers, but don't send it to settlement-free peers. Some of the common transit provider communities, often transit providers will offer a community to set local preference. They'll offer a community to prepend the transit provider's AS towards peers. They'll advertise route containment communities. For example, don't link it to peers, don't leak it out of the continent, don't leak it out of the country, don't leak it out of a particular region, don't leak it out of a particular state. Some providers will offer this behavior targeted to a short list of autonomous systems. For example, you might say, don't send it to peers of Sprint, or prepend twice to peers of UUNet. Community stripping. So there's some default behavior differences on the different router vendors. By default, Juniper will send all communities. So if you don't want a Juniper router to send all the communities on the route, you actually have to write policy to strip those communities off. In the case of Cisco, it doesn't send any communities by default. If you want a Cisco router to send communities, you have to issue the send community config bit to get it to start doing that. And generally on the internet, when people peer, they don't want their peers to do traffic engineering on their local network. So they'll generally flatten all of the meds and strip all of the communities. So you can assume that if you're putting a community on a route, as it goes upstream through transit providers, it will probably stay there. Once it goes to a peer, it's probably gone. Aggregator is an optional transitive attribute. It's used when a router receives one or more routes that it aggregates into a supernet. And the aggregator is the router ID of the router performing the aggregation, which is useful for troubleshooting to figure out where this aggregate route is coming from. The aggregate route can also inherit some of the qualities of the contributing routes, like the AS path, and it'll store them in an AS set. And you can craft policy to say certain routes do or don't contribute to the aggregate. So the way this looks in a drawing, we've got AS1 advertising 1.1.1.0/24 and AS2 advertising 1.1.2.0/24, both to the same upstream AS3. In this case, AS3 is going to aggregate those 2/24s into a 22, which is 1.1.0.0/22. And he's going to advertise that to AS4, his upstream. So one way he can do that is just simply advertise the /22, and it will be originated by AS3. But another way that he can do that is he can use an AS set and inherit the AS path of the contributing routes. In this case, you'll see that the routes are being originated by AS1 and 2 behind AS3. There's also the atomic aggregate. In this case, AS1 is again announcing the same /24, but AS2 is announcing the entire /22. AS3 is only going to announce the aggregate /22. It's going to show that as being originated by AS2 behind AS3, but it's also going to set the atomic aggregate flag. So that's going to indicate to upstream routers that AS3 sees other more specific routes inside that /22 which are being suppressed. One more path attribute, the AS4 path. The AS path is actually not capable of carrying 32-bit autonomous system numbers. There was some discussion about changing the AS path to include 32-bit ASNs, but that would make it non-backwards compatible and break the already deployed implementations. So what they decided to do is to create a new AS path called AS4 path. And in the AS4 path, they would put the 32-bit ASNs. And they would still continue to put the AS path, the 16-bit ASs in the AS path, but in the event that there was a 32-bit ASN, they would stick in AS23456 as a placeholder to indicate that there was a 4-bit ASN that couldn't be properly represented in the AS path. So this way, routers that weren't capable of a 32-bit ASN could still just use the AS path. Everything would work just fine, and they would see AS23456 in the AS path. But routers that were 32-bit capable would actually be able to use the AS4 path and see the 32-bit ASNs in there as well. There's some interesting interaction here because you could have a router in the middle of the network that is only a 16-bit ASN capable, in which case when he appends his AS to the AS path, he's going to only do that in the AS path and not the AS4 path. So potentially the AS4 path does not contain a complete view of the AS path. So you have to construct a complete view of the AS path both from the AS path as well as the AS4 path. And that's going to be the case for some time until all routers are AS4 capable. Do you guys want to take a break? Say 10-minute break? All right, let's go ahead and take a 10-minute break. withdraw this now.
Okay, well,
Okay. I saw an email from that, yeah.
Yeah, I don't know if there's gonna go or not, but I think this was
Oh, then I'll mention it to her and see if she wants to. Figure out. I'm just thinking find a piece of paper to draw this.
you don't even need to draw it. All comes in shapes. So we have a very important focus on every training authority. So one way is that you have a failover, so you just everything ready, standby, ready to go, and just advertise the stuff over there. Boom. So take the Linux failover. Yeah, fortunately we don't have to.
So there's a question
Advertise the address both
about,
simultaneously.
is there active content on the server? So that if somebody hits that server, suddenly switches over to the other server.
It's all fed out of the database.
Is the database shared across both sites simultaneously?
It's on the back end. Is the LAN. The database is the whole LAN. We have a standby.
Standby has exactly the same data as the packet.
So, but it's not active, it's in standby. So the DBA will disrupt it. And then the servers in Clearwater will be accessing it, and servers in down the road, there's a logical information that site runs in this site. It takes time to get there. So the real solution is to have the IP active in both places simultaneously. And the databases with the logical. But in the short term, you would have a failover.
So one of the reasons for the failover.
One conditional route site, so
Is that traffic coming from?
so like inject a big route, and if that route disappears because the list stops, you need to advertise that figure it out.
Yeah, or you could advertise them as less preferred over the standby server. They both have different upstream providers.
Well, this is where another reason why you can line up with clear one, we have
Yeah, let's talk after the session. Yeah. Yeah. So for me, there's actually a forming So if you have a 4-byte ASL, then you're No, if it's looped. Right. One doesn't loop the other. Yeah, you don't care if other ASs show up multiple times. You just want to Pretty much, yeah. Yeah, we're gonna go ahead and start one of these. Yeah. All right, we're going to go ahead and get started back in a minute. Yeah, I was going to start a few minutes early, if it's okay.
Yeah, I'm not sure if people are actually going to try to connect over for this one, so.
We got to wait till 4? I can.
Yeah, I think that might be better for me to have a discussion or something. I'm not sure. What's your experience? People.
That's the first time I've done this.
Okay. How about maybe, when's the break? 3:30, right? Let's check what else is going on right now. Yes, I would say at least for 3:30 maybe. Okay, right, so these guys.
Well, then there's going to be a break anyways.
So you think this is better?
Imagine if they not getting some bigger call.
Yeah, let's maybe start at 12. Yeah, let's do that. Alright, then.
That's right. So I've actually been asked to hold off on the 102 slides until 4. So if anybody had any questions or wanted to review anything in the first half, we can go ahead and do that. If not, you're free till the next 15 minutes, and then we have a break and some coffee and cookies and whatnot. Yes?
Are your slides available on their website?
They will be available on the website, yeah.
Do you see, like as like 10 gig is like something more prevalent, like using like fiber channel over Ethernet for multiple sites more prevalent?
So the question is 10 gig becoming more prevalent, and are people using
As it becomes more prevalent.
and are people using fiber channel as it becomes more prevalent? So, yeah, certainly we're seeing a lot more Ethernet, a lot more giggy and 10 giggy. A lot of the reason for that is because it's cheaper. You don't have all the timing, clocking, sonnet stuff. And certainly as growth of utilization grows, people are wanting to bond those together. So yes, we are seeing that. All right, well then I guess I'll see you all at 4 after the break.